Dr. Xian introduced me. One was my main theme, research theme is the intervention, especially structure intervention. But also, the structure intervention is one of the technology for civil engineer to achieve SDGs or carbon neutrality. So I put together into two issues today. So the beginning part, I try to introduce my collected information, how civil engineering or building structures would contribute in both ways, positively, negatively, to SDGs. So we have two aspects. Yeah, as a civil engineer, you can be proud of it. We can make a great contribution to SDGs. But at the same time, we should not forget we have negative impact as well. So this is everyone knows UN logos. SDGs 17 goals. Can you, any one of you, name all the 17 goals without seeing this one? It's quite difficult, right? Yes, I know. Yeah, this is a bit small letters, but this is the 17 goals. Okay, so it's about various issues, something like zero hunger, quality education, gender equality, but at least 9, industry innovation and infrastructure. From the name of the goal, you can tell this is somehow related to civil engineering, but also sustainable cities and communities, also closely related to civil engineering. The climate action, yeah, this is net zero, carbon neutrality. But what I'm going to tell you is something more. Once you say sustainability, most of people, you think about the environmental issue. But in fact, sustainability is quite a broad concept, which has the 3 pillars: social sustainability, environmental, and economic sustainability. I encounter this topic. This is an economist, so it's not a document in civil engineering field. But in this report, it says infrastructure plays a key role in all 3 dimensions. What I said, social, environmental, economic sustainability of sustainable development. And one of the infrastructure's most important role, increasing resilience, runs across all 3 of the 3 pillars. So the even economist, this big publishing company, they know civil engineering or infrastructure is very important. This is another paper which you can find in the Nature Sustainability, Infrastructure for Sustainable Development. This paper, they look at very in detail how infrastructures can make contribution to the SDGs. As I said, SDGs, we have 17 goals, but after the goals, under the goal, we have targets. Target shows more quantitative way how to achieve the goal. So in altogether, 169 goals. Then each small figure is indicating black part. Infrastructure can directly influence to achieve such particular target. The gray one somehow indirectly influence to achieve such targets. Then altogether, 72% of target is influenced by infrastructure. Okay. Then you can see all the gray part. You can find all of 17 goals, even gender equality. quality of education, how infrastructures influence those goals. This is a more related document in civil engineering document. The author is Andrew Vinson, Global Cement and Concrete Association. This is international industrial organization for cement and concrete industry. He examined very precisely how concrete or concrete structures influence every one of the 169 targets. Then his conclusion, of course, are his own analysis, not also I think some government was on UN, but 48%, nearly 50% of the 169 targets will be influenced by concrete or concrete structures. Then how gender equality can be achieved by concrete or concrete structures? How education quality can be achieved? This is one of the examples. In many developing countries, in the school, they don't have clean toilet. Boys, they don't care, but the girls, they're ashamed to go to school because they don't have clean toilet. So concrete as one of the inexpensive material, together with the bricks, you can build clean, neat toilet so that our students can go to the school. It's good for the gender equality and the quality of education, something like this. And this is another paper which my former master student, Wan Lee, founded. And this paper summarized from year of 2000 to 2017, not really latest statistics, in the Web of Science papers. How many papers are dealing with infrastructures and SDGs? Then this is the total number of papers. Of course, naturally, in recent years, more papers talk about the infrastructures and SDGs. Interesting. China is a country have written this kind of paper most. So China paid quite big attention to the SDGs already. The same paper, they look at those listed papers in different aspects. Which pillars they're looking at, social, economic, or environment. In the past, sustainability means only environmental issues. So most of the paper look at environmental issues, not economic issues, but social issues. But this is quite, I think, natural. Another aspect, once you look at the structures, which stage of your structure? Like a planning stage, construction stage, usage stage, demolition stage. Of course, none of the paper look at all the stages. They particularly look at some stages. Many papers looking at the planning stage and execution stage, construction stage, meaning that what is the construction material used, this kind of thing. But they don't look at the stage, the use stage or demolition stage, even though in fact those stages are quite important, but so far not many researchers pay attention. Okay, that is so far positive side, but we have to pay attention to negative side. This is a Guardian, another big publishing company. A few years ago, they published this article. Among my community, my expert in concrete, everyone knows this article. It criticized concrete. Concrete is some substance which really affect net zero. So it's quite true. The annual production of concrete, 29 billion, nearly 30 billion tons, which is equivalent to 433 gorge dams, which is largest concrete dam. Then such amount of concrete needs a lot of material, like 74 billion tons, water 2.3 billion tons, fine and coarse aggregate over 10 billion tons each. So we need a lot of material resources. Especially, I have to emphasize China. I think this statistic, I don't know, it includes Hong Kong or not. China, only single country, their construction market is more than 50% of worldwide construction. So China is really constructing a lot. I also observed last 2 decades, China prepared express highway network nationwide and the high-speed train network nationwide. Only 2 decades. The total length is 10 times of Japan. It took Japanese 50 years to have such network, but China did only. Bullet train, 10 years. Highway, only two decades, 20 years, meaning they really had a lot of construction. CO2 emission. Concrete is one of the important items for CO2 emission. Firstly, building and construction occupy significant proportion of global GHG emission, 40% coming from building and other structures. Not only construction, but also during the operation. Then building and other construction works emit 13%. So during construction, which is responsible for civil engineer, and operation of buildings and others emit 27%. Yeah, after the construction, during usage stage, we emit a lot of CO2. Then this is another way to look at the CO2 emission. The sector in different categories. 6% from cement, 8% from steel. Cement, 100% for construction industry. But steel, not only construction industry, yeah, majority construction, but also other industry. So cement is quite big component of CO2 emission. So we have to take some serious measure as a civil engineer. This is another way to look at the CO2 emission by country. Yeah, naturally, as I said, China is the biggest construction industry. So China is the most. They are extremely, followed by US, EU. And this is another way to look at CO2 emission per unit economic activity. Of course, how much CO2 emission really depending on level of your economic level. Also, it reflects the technological level. But still, China is high. But something good news for China, that CO2 emission per unit economic activities, China reduced drastically in recent years. Its latest figure in this diagram is of 2017, but the real latest statistics, level of the CO2 emission per unit economic activity is very similar to EU, Europe. So China really developed relevant technology, and in this sense, it's almost same as developed country. I found another interesting book. it shows how China need challenges to achieve net zero in terms of the energy. Then probably you know, China is the best country for wind energy and the solar energy. Extremely big energy production. But also, China itself has some difficulty to achieve net zero because of the coal summer power plant. You still need a lot of electricity coming from the summer power plant of the coal. Then, if you compare with the United States, CO2 emission from the transportation in China is much smaller than US. Similar size of the country, but the transportation CO2 emission in China is much smaller than US, meaning you have rather good public transportation compared with the United States. Carbon neutrality, in terms of the size of the construction project, this analysis indicate if you have bigger project in terms of the money, your CO2 emission also become bigger. It's quite a proportional relationship. This information is given by the World Economic Forum, Net Zero Industry Tracker. They picked up some industry, including cement and steel. What is the key issues to achieve net zero by 2050? Then they have the 5 important factors. One of them is infrastructure. Infrastructure is quite important for those industries to achieve net zero. So this is more precise analysis. Steel and cement industry. Green means they are ahead, rather advanced stage. But cement and steel mostly red and orange. So it's quite still primitive stage. So we have many things to solve. Then carbon neutrality for concrete. In fact, concrete is a source of CO2 emission, but also we can make a lot of contribution to reduce CO2. This is very small summary of the available technology, how to reduce CO2 emission, or even concrete can absorb CO2. Concrete material as a white carbon, summarizing those relevant technology, we call it white carbon. And the reduction by replacement, utilization of non-Portland cement materials, and limestone calcinated clay cement, capturing, and the concrete hardening by CO2, producing aggregate by using CO2, production of CaCO2 by using CO2. So we can utilize CO2, make some substance or new type of cementitious material. And also we can have the 100% recycling system utilizing CO2. Absorption of CO2 make recycled material with more higher material property. And at last, I can say every concrete absorbs CO2 naturally. So every year, about 1 billion tons of CO2 is absorbed by concrete itself. And this one is the provided by Global Cement and Concrete Association. how concrete and the cement industry to achieve net zero by 2050. So according to their scenario, a quite big portion coming from the life cycle management, good maintenance, good intervention. This is what I'm talking about later today. And also, as previous slide indicate, some material technology, capturing, CO2 capturing new material, and also storage facility is also, we need a concrete. So altogether, somehow they believe we can make net zero by 2050. And this is a slide for steel. I'm not really expert in steel, but also steel industry. They have the lot of relevant technology. Reducing CO2 emission during steel production using hydrogen rather than coke, using green electricity, capturing CO2 using recycled steel. Yes, in fact, the steel is very, very recyclable material compared with concrete, cement. And steel itself as a part of main material for infrastructure. So all the relevant infrastructure to achieve CO2 emission zero, we also need a steel, definitely. Then this slide shows, getting to the my main agenda today. So far, what I say, like cement industry technology or steel industry technology, this is only this stage, production stage. How you reduce CO2 emission during concrete production, cement production, steel production. So this is so far their main concern. And during construction stage, yeah, we also emit the CO2, but compared with other stage, it's not so great amount. But also at this moment, we have many studies how to minimize CO2 emission during construction. But we don't have much studies on this during use, right? Building and the other infrastructures, their life is 100 years, more than 100 years. During that period, naturally, we have a lot of CO2 emission. For the construction site, we have repairment, refurbishment, right? Some maintenance. It's also part of kind of the construction work. So we have to consider carefully those maintenance plans so that we can minimize CO2 emission. And at the end, we have demolition. We don't have many studies how to achieve better demolition to minimize CO2 emission and also utilize recycling, reuse more efficiently. We need more studies in these stages. So this is a diagram which shows, as I said, right, during cement production, we have a lot of CO2 emission. But at the same time, during some slide, we have one intervention, another intervention. That is kind of construction work. So we have another CO2 emission. But we only pay attention to this. We have to have overall scenario so that you can optimize or minimize CO2 emission. This slide shows another aspect, maintenance intervention in several countries. This is from Japan. In fact, this kind of statistics, it's quite difficult to find, but fortunately I found it in several countries, only 3 countries. I haven't found a similar statistic in China. But from Japan, each bar height indicates construction market site, domestic market site in Japan. So the mid-90s is quite big construction market in Japan. At that time, Japan was #1, bigger than US, bigger than China. But after that, our construction market became very, very small. Yeah, I don't have to talk about it much. This is also fact. Then this light blue is a new construction. The green is maintenance. So you can see most of the changes coming from the new construction. But the green part is quite steady, and in fact, slightly increasing recently. So meaning, as a nature, we spend more money, more project for maintenance repair. So recent years, about 30% of construction is maintenance repair. This is Korea, South Korea. This is only road infrastructure only, okay, not overall. We have last century, yeah, the construction market for road is increasing, but in the 20th century, it's become stable. The blue one is maintenance repair. So maintenance repair is also around 30 or more than 30%. So it's indicated our construction market. About 1/3 is maintenance repair, and 2/3 is a new construction. As a civil engineering student, you pay attention mostly new construction, but quite big percentage is going to maintenance repair. And UK, this is a country, I believe, they developed the infrastructure nationwide first, probably. There are subways since 19th century. Many, many bridges. Their first steel bridge or iron bridge is 250 years ago. In such countries, we still need a new construction. They nearly need to reconstruct old construction structures. But this orange part is maintenance. So this country, UK, about 40%, nearly 1/3, is going to maintenance repair. So this indicating most of the countries like China and Japan, their future is something like this. So about 40% is maintenance repair. Then coming to the Japan Society of Civil Engineers. I have been involved in this society for many decades. And the recent years, we have some activities for the carbon neutrality. So this is indicating current technical activities related to carbon neutrality. Many technical committees, they are looking at carbon neutrality in different aspects. And also our monthly magazine, one time, about nearly 4 years ago, they have the special issue of carbon neutrality. And the AIJ, this is Architecture Institute of Japan and Japan Society of Civil Engineers, two big organizations in the construction field. We have collaborative work on the carbon neutrality. And sorry, this is in Japanese, but it is in a special issue in the JC monthly magazine, how carbon neutrality can be achieved by 2050. This is the general overall scenario. And this is indicating how civil engineering can contribute carbon neutrality in many aspects industry, mobility, town, home, energy, and others. In many aspects, civil engineering need to contribute for carbon neutrality. Then also JC, 3 years ago, they published one small booklet to show how society or nationwide social system related to infrastructure or civil engineering. It's kind of the nationwide community network, including transportation or so on. Then they are saying we have to provide foundation for achieving sustainable society, bringing well-being and symbiosis as well as carbon neutrality. The JC, as a representative organization, we show the Japanese society to how our future landscape should be. Then this is another information. Carbon neutrality is not free. We have to pay additional cost. Then several articles say we need to say something like a 5% more cost compared with overall the economic activities. So we have to pay few percent to the 5%. This is additional cost to achieve carbon neutrality. Then this is summary contribution infrastructure, life cycle management of structures for carbon neutrality, green materials, execution, maintenance, intervention, demolition or so on, and the infrastructure. So the summary, how structures, civil engineering can contribute. First one, life cycle management. Good maintenance, repair. And also green materials, execution, and the demolition, and so on. And also circularity. And also infrastructure itself, we need it to achieve carbon neutrality. Lot of infrastructure, relevant infrastructure. And also transportation system. Yeah, this is not today's issues, but we have some transportation system which is suitable for carbon neutrality, and the national land planning. It is community network, how we allocate big cities, small cities, and how are they connected, this kind of thing. So this is my main issues. Extension of service life of structures. Once your service life becomes 3 times longer, then carbon emission, CO2 emission becomes 1/3, right? Then recycle and the use of concrete and utilization of the industrial waste and the concrete material. We have various aspects, but today we're talking about the repair and the strengthening and the structures. And this is somehow relevant technology, very small summary. To have a good maintenance, we have to predict your service life. How to predict your service life of structures. And also assessment of the current structure performance. You need a good inspection system. Recently, we have a lot of relevant technological advancement. And I don't have to say, once we have provided maintenance-free material, very highly durable material, of course, it's also good. And this is showing some typical structural interventions, which I'm talking about today. We have various ways of the interventions using different materials. We have so much varieties of structural intervention with different materials and the different structural detail. So, such as FRP is one of the strengthening material. Mechanical property FRP, high strength, low stiffness, no UV. So this is quite different from steel. And also, we have several FRP materials that are among the different FRP, their properties also different. Failure mode is also different from ordinary reinforced concrete. Once you use FRP, reinforcement, the breakage will become failure. And also, once you have the external bonding, the bonding is another failure mode. So they are different from ordinary steel reinforced concrete. Then we have several key issues. Shear strength and ultimate deformation, debonding, long-term performance. If you are familiar with the shear strength of the reinforced concrete member, you can tell this is the shear strength of the concrete member. Then we have concrete contribution and steel shear reinforcement contribution like this, but they are all empirical formula. I think any country in the world. Then some of the things, this is representing effect of reinforcement stiffness. And this is indicating stress remaining after using. But this kind of the empirical formula, it's only applicable to the steel reinforcement. Once you use the FRP, this formula cannot work. Then we have the jacketing like this. We jacket or wrap tension material surrounding concrete. Then we have some confinement effect from the wrapping material, which does not exist ordinary concrete structure without wrapping. Then for the seismic performance, we have to know what is the ultimate deformation, but we don't have really commonly accepted model to predict ultimate deformation, which is quite important for seismic design. Then external bonding case, we have several debonding modes. Not only one mode, we could have debonding here, or we could have debonding, we call it the concrete separation, or we could have debonding like this. So each debonding, different type, different mechanism. So it makes it very complicated and even more complicated. Even though debonding happens at certain location, it can be central part of the beam or end of the beam, but you have to be careful where debonding takes place. Debonding takes place adhesion interface or within substrate concrete or adhesion material itself or within strengthening material itself. So you have to look at very carefully where the bonding location is. So in fact, the bonding is very complicated. Then long-term performance, I talk about only with this slide today. we don't have much information. Like FRP, yeah, this is one of the main material, but we don't have accumulated knowledge or information for long-term performance. Probably only available data is 30 years exposure test. So we don't know 50 years life, 100 years life of the FRP. And not only material, like the bonding interface property, we don't have much information. Long-term performance interface behavior. Then the first issue, shear strength and ultimate deformation. This is various tension reinforcement. This is steel and carbon. Quite different stress-strain relationship. We try to utilize it for the reinforcing material. Then carbon, high strength, high stiffness. Another extreme is a steel, low strength and low stiffness. At the middle, you have some medium size of the strength and smaller stiffness, medium size stiffness. Then what I can say is high strength material usually expensive. Lower strength material, less expensive. So high cost, low cost. But you shouldn't forget this point. High strength, but fracturing strain is very small. Low strength, usually fracturing strain is very high. In fact, not only strength, we have to utilize fracturing strain. Stiffness strength can be replaced by smaller strength and stiffness material if you provide a more amount. So in fact, high strength material is not absolutely necessary. But if your design says we need a deformability of the material, small deformability of material cannot be replaced by highly deformable material. So deformability is one of the key issues for seismic performance. Then high deformability could be a better option than high strength and stiffness in terms of the seismic performance. Then some new retrofit method, durable and low cost, and fiber material with high deformability, based on the shear reinforcement. Yeah, in fact, what this TV camera shows. It's okay?
Yeah, yes, someone is working.
I see, okay. Like this one, this is specific carbon like this, steel like this, but as a shear reinforcement, we need some big fracturing strength to achieve shear reinforcement until the end of the ultimate deformation. But the steel, it doesn't break, but the stiffness becomes very small. So to have a good shear reinforcement effect, stiffness is also important. But it cannot break like a carbon. So material, something between steel and the carbon is the best option for shear reinforcement. Then this is knowing this fact. We utilize highly deformable material, putting hinges on, which needs a more deformable material. Then once we use the deformable material, which is PET fiber. Your PET fiber is this PET material. We can have better seismic performance. like this. So specimen with a PET fiber, better typing performance than the carbon, reference specimen. And that specimen with a PET fiber like this, and the carbon is like this, and the reference specimen like this. So if your shear reinforcement doesn't show the breakage, this is perfect. But you better have still rather high stiffness. So steel reinforcement, no breakage, but yielding. So the stiffness must become much less. So this shows some experimental result. Yeah, this PET fiber, even deform greatly like this, but no breakage. If this is the carbon, definitely carbon break. And the PET fiber cheap, you can understand, right? This PET photo is not expensive. So the PET fiber is much less expensive than carbon, ceramic. So the construction cost, material cost is cheaper. So in Japan, we have PET fiber real application like this. So optimal property, not only stiffness, but also deformability. This is quite important. Then to deal with this kind of the different type of the mechanical property of the material, we need some generic model. So to have generic model, yeah, our research group proposed some model which can predict shear strength and also shear deformation model. Yeah, probably I may not go in detail. And also friction strength model and the friction deformation model. So we combine using considering each material stress strain relationship, and we utilize typical sectional analysis, and we consider contribution of each component for the shear strengths. Then we have the concept of the potential shear strength depending on the deformation. So once we have greater deformation, meaning greater strain development and less stiffness, then remaining shear capacity becomes less. And we also consider shear deformation utilizing simple truss analogy. Then also we can consider tension shift in the tension reinforcement, which produce additional friction deformation. Then this is a model prediction. So our model predicts, except this case, quite nicely for post-peak read. So we can predict ultimate deformation, which is necessary for seismic design. And this is a prediction and the experimental result agreed. So second issue, debonding. In fact, debonding takes place in concrete or real interface or this adhesion layer and the tension material interface or within tension material. Anywhere, in fact, the bonding takes place. Then we have a lot of studies in the bonding, but they may not pay attention where the bonding is happening. So this one, the bonding at the surface layer of substrate concrete, we call C1. This is some early contribution of the Professor Dai Jungo. He proposed this formula for his PhD study, in fact. Then, based on his study, in fact, better debonding strength come from the softer adhesion layer. So, softer adhesion layer in a low carbon stress relationship showing much higher peak on stress. But this one is substrate concrete debonding case. Okay, this is only true for substrate concrete debonding case. Then, knowing this fact, some technology was developed using quite a low thickness of the diffusion layer, such as resin, so that you can have better, higher debonding strength. So softer diffusion layer is one of the way to increase debonding strength. Then come into another debonding failure mode, debonding at the diffusion interface between substrate concrete and the diffusion material. So we have another study looking at the bonding strengths here to cementitious material failure. So in this case, the bonding takes place clearly at the interface between two materials. In this case, concrete strength and the interface roughness is main factor. Once the bonding takes place, clearly interface between two materials. All right, previous case, that is the bonding takes place within substrate. If the bonding takes place within substrate concrete, roughness doesn't matter. But at the real interface, roughness does matter. So this is the experimental result. So roughness increases, the bonding strength increases. But once roughness reaches certain amount, like about 0.5 millimeter, then the bonding strength becomes constant. Another interesting thing, if you have high strength concrete, this bonding strength becomes smaller. Because in this particular case, polymer cementitious mortar. Polymer is one of the mechanisms to strengthen interface strength. But polymer cannot penetrate into the concrete if high strength concrete. So to have the better penetration, lower strength concrete is better. The lower strength concrete gives you higher bonding strength. It's something surprising. So again, strength doesn't work. Then this is the case. Yeah, this is a external bonding FRP sheet. FRP sheet case, usually the bonding takes place substrate concrete. But substrate concrete strength becomes very high, like 90 megapascal. Then the bonding takes place at the interface, a diffusion interface between a diffusion material and substrate concrete. So if this is the case, roughness does matter. Greater roughness gives you higher bonding strength. This is different from the Ueda case. Ueda case, substrate concrete debonding. But this one, a diffusion interface debonding. So surface roughness only affect in case of real interface, a diffusion interface. Right, going the bonding at the diffusion material layer. So the bonding takes place this time within a diffusion layer, within this one. Then what happens? Earlier, as I said, if the bonding happens in this substrate concrete side, softer a diffusion material layer gives you higher bonding strength. But if the bonding happens within a diffusion material layer, softer material gives you smaller bonding strength. So again, it depends where you have your bonding takes place. So you can get completely the other outcomes. This case, soft adhesion material layer doesn't work. But this case, if substrate concrete the bonding takes place, soft adhesion material layer does work. Okay. Then even this case, if both sides is very high strength, so the bonding takes place within adhesion material layer. In this case, usually this is the polymer. Polymer is confined, restricted, its shrinkage. So it's become introduced, pre-stress is introduced within material layer. So it's affect, reduce the bonding strength. So we have many other aspects as well. Then this is a debonding case in terms of the concrete dry fiber fabric piece with cementitious material. In this case, debonding takes place within adhesion material. In this case, adhesion material is a cementitious material. Same as substrate concrete. So if debonding happens within cementitious material, like concrete, then the bonding nature is similar to first case. So you have to be very careful where your debonding takes place. The last one, debonding at the adhesion interface between adhesion material and the strengthening material. So this time, here debonding takes place between tension material and adhesion material. So in this case, I only found the one case. This particular case, the extent of cementitious material impregnation into the fiber bundles is one of the key parameters. More impregnation, the bonding strength becomes higher. So you have to be very careful where your debonding takes place. The controlling parameter is quite different in each case. Your conclusion may be completely wrong. So you have to be very careful. And some other debonding issues, external bonding issues. The first one, two issues here. First one, I briefly introduced. Yeah, debonding is a main issue, but recently, collaborative study, Japanese university and Japanese company, they found the external bonding of the carbon fiber sheet, but we can completely prevent the bonding. How we prevent the bonding? Now, this is the usual way, external bonding like this, steel plate attached to the tension face. And the better way, we call it the NSM, near surface mounted. So we make a small ditch like this, groove, then we inserted the tension material. But even NSM, you cannot avoid the bonding. But our new technology, we fold sheet, like this sheet, fold it like this, fold it like this, then insert in the groove to increase interface area. Then, result, we can avoid debonding. So no debonding. Ultimate failure mode is fracture of the carbon fiber. Not only the poor test, but also beam test. Ultimate state is the rupture of the carbon fiber sheet. So it's a perfect 100% utilization of the carbon fiber strength. So we are successful to avoid the debonding. Then our proposed technology is like this. This is Japanese product. I think in China, I found some similar product but not really practically applied yet. But each sheet consists of a composite of very small CFRP bar like this, and they are connected each other to make a sheet form. Then we fold this sheet, we call it the carbon fiber strand sheet into the roof. Then we make a NSM. By doing so, this is our proposed way. So rupture of the carbon fiber, the ordinary external bonding way, the bonding takes place. As earlier explained. Then this is a strain distribution. So much higher strain developed, meaning much better bonding performance. Some who know the local stress strain relationship, it may be surprising to you. This is ordinary carbon fiber sheet with relationship, but our new technology much higher local shear stress. So this is some construction process. And this is a result of the beam test. And we also conducted fatigue test. Even fatigue test, we prove better performance. And not only flexural reinforcement, also we utilize shear reinforcement, then we can avoid the bonding. And in this particular case, increment is not great, but our new proposed technology in SMC phases achieve better, higher shear strength. Then we can utilize this technology to strengthen this part for shear reinforcement for the T-beam like this. One more newly developed concept. For repairment, this is ISO document. We have many intervention principle or remedy from 1 to 12. We have the different purposes: protection against ingress, or structural strengthening, or this kind of thing. Measure for concrete defect deterioration, measure for steel reinforcement, explosion, and strengthen. Then, new concept is one particular repairing method, we can achieve more than 2 remedies. For this particular case, using carbon fiber fabric, we can achieve structural strengthening, like strengthening, which I have been talking about, and also it can be used the cathodic protection. So dual function. Then we conducted many experimentation to prove cathodic protection does work, but we have some degradation. Instead, due to the ICCP, impressed current deteriorate carbon fiber itself, in fact. But somehow, fortunate part is once you have chloride environment, deterioration become much less. It's something good news. Then we conducted various experimentation that right top here shows some cathodic protection does work, and also some bone test. We observe some deterioration, as you can see here, but once we can predict how much deterioration we have, we can have nicely designed. And also we conduct many beam tests, column tests, And also we have some practical application of this ICCPSS. So this is a new concept, dual purpose. I never seen something like this. All the repairing method on the single purpose. But this is dual purpose. This is also another new direction. Then my last issue is standardization for life cycle management and carbon neutrality. Yeah, life cycle management is still a new concept in our structural engineering community, civil engineering. Also, holistic framework, the carbon neutrality, we have to achieve carbon neutrality, but in the civil engineering field, we don't have really well-developed system of CO2 emissions, especially during the life cycle time. Then to avoid such, to improve current situation, standardization is necessary to assess the accuracy and the reliability to show the standardized method. Yeah, at this moment we have too many methods for repairing. We should have some standardized. Then lack of reliability due to lack of data, too many interventions. So big variety of structure detail, big variety of structure material. That's why I say, what is optimum material property? We don't know yet. No? The long-term performance, which I didn't talk about today, but we don't have data at all in many cases, especially interface. So we need a standardization standard to assure the reliability to show the standardized method. Then for this purpose, ISO, this is the International Standardization Organization. Then one technical committee dealing with all kinds of the concrete issues. In fact, I'm chairing this technical committee at this moment. Then subcommittee 7, maintenance repair, SCA, environmental management, like carbon neutrality issues, and working group 1, life cycle management. So concrete community in ISO, we put the best effort to have the international standard. Then this is some recent example, life cycle management concrete structure. We already have some ISO document available. The maintenance and repair of concrete structures we have available. And this is some kind of the umbrella. Then this is the particular repair structural strengthened interventions, ISO code, using cementitious material. As I said, external bonded cementitious material. Some ISO document available. Then FIB, this is the International Organization Structural Concrete. May also put the effort to have the code, Model Code 2020, just published 2 years ago. The first international standard for both new and structure. In Hong Kong, do you have any standard to deal with both existing structure and new construction? I don't think so. We have received such standard, but FIB model code, it covers both. So it contains a lot of intervention and the maintenance issues. Yeah, if you have some interest, please purchase the code. Then FIB also published several technical documents, recent document related interventions, such as 102, 103, and something 90. 90 is FIB. So this is my last slide. So I believe I could convey civil engineering quite responsible part of the world to achieve SDGs and carbon neutrality. Then longevity of structure life is most efficient way to achieve carbon neutrality and SDGs. The structure intervention is one of the efficient life cycle management activities, measures, but optimal material property and the characteristic is maybe you don't know yet, which may be quite different from your ordinary concept against the reinforced concrete structure. Then international collaboration, including international standardization, is quite important. I believe that China's responsibility is quite great. Thank you very much.